Okay. Okay, very good. So thanks a lot once again to those of you who basically survived until the end of the conference. And well, I intentionally put my talk the last one so that if you're upset that I'm taking too long, then it's all my fault. So I will be talking today about this cold starting. I don't know if you can hear me like that. Is it fine? Probably I should make it a little bit higher. Okay, so I will be talking about cold starting of reservoirs in the particular task of forecasting of dynamical systems. So what I mean here is that there will be this joint work that we started together with Juan Pablo. We were contacted by Yannis Kevrikidis and his postdoc, Felix Kemis, whom you see here in this long list of co-authors. And eventually this basically led us to being able to obtain something which we submitted first to the proceedings of GSI, and now it's getting longer, so we probably will publish it as a longer version of the paper and should be available as archive paper probably within 1 month. So what I will be doing here, I will be showing you a couple of, let's say, tricks how we could put together what we have done earlier, and Juan Pablo, he already advertised some of the work that we have done earlier on so-called generalized synchronizations together with Alan Hart, and we will find a way how to put together what we have done earlier with the work of Yannis, Felix, and then other people joined us in our attempts. So let me first start from the following observation. So probably you don't need to look much at this slide as a whole, but I will be deviating from learning input-output systems in this talk. I will be still staying in the agnostic environment. So what we mean by that is that we're trying to reconstruct or learn an unknown target out of some partial information. And here I will be placing myself in the setting of dynamical systems. So what our goal will be is, well, to learn dynamical system out of low-dimensional observations of it. So basically target dynamical system may be defined on some manifold, which may be high-dimensional, and then we're observing only low-dimensional observations of it. And then we will be presumably working in the setting when we have only finite observations, or finite number, or short history of our observations. So in this setting, let me just remind what Juan Pablo already introduced in his keynote talk. We are calling reservoir systems such state space systems, where what is important for us, so this is a definition that you have seen yesterday. For us, what would be important, probably these two letters, right? F and H. So F is a state map or reservoir map that defines basically a state dynamics. So given some elements of the input sequence Z's, we are, well, collecting or listening the states X whenever we know or we define this kind of reservoir map or state map. And then we're projecting or collecting those states using the readout map, this is how we call it, this H, into our target elements of our sequence. So what is important here is that these properties of this F and H will be what will be defining the reservoir computing systems, and we will be calling such state space systems reservoirs whenever some ingredients of this F, so F can be, for example, some nonlinear function, and then it will be defined using some kind of, for example, with the help of some random matrices drawn from some regular distribution. So what is important is that ingredients of that map should be randomly generated, and model fixes them basically for good and never trains them. So this is non-trainable part, and the only trainable part will be our readout. So if I'm looking at this kind of a system, so one example that Juan Pablo already gave you in his keynote is this eco-state network. So probably that's one of the most popular families of reservoir computing systems, because it relates notion of reservoir computers to recurrent neural networks. And here what is important is that we're generating this A, C, and zeta randomly. So sigma can be some kind of a squashing function. Think of, for example, continuous bounded non-decreasing function. And then this W could be this readout map that I showed you earlier. This will be subject to training. So if we're taking the squared laws, then we will have a closed form solution. So probably that will be linear regression, which is regularized. So for example, L2. So what is important in this kind of a system, if you look at it carefully, is the fact that actually if you even generate this A, C, and zeta randomly, there will be still some ambiguity about the initial state. So if you imagine working with the state space systems of large state space dimension, a couple of thousands, this is what people use in literature. then probably you will have to wait for a long time until the system converges to a stationary regime, which would mean that you will be well constrained about how much of an inputs you should have in advance before you start your modeling. So this somehow rules out this initial plan of using short history in the training. So if I'm thinking about neural networks in the standard case, the same type of problems people are coming across. So for example, they worry about estimating also A, C, and zeta. That would be an example for classical recurrent neural networks. And then people worry about how to initialize the initial weights so that you are getting better properties of convergence for your stochastic gradient descent. So in particular, in this picture, you can see all different heuristic choices that people make. If you work with, for example, sigmoid activation, or you work, this is just static deep neural network, you work with TANH or you work with ReLU, then people come up with Xavier, normalized Xavier, Hare, different types of initializations where you basically in each next layer, you're modifying the support of your distribution that you're choosing to initialize your weights depending on the number of neurons in the previous layer. So that is why you have these kind of pictures, and here you would use uniform distribution with a corrected support, and here you would use some kind of a Gaussian distribution with a corrected variance. So we will try to relate this problem now of initializing the initial states of the system together with the classical embedding strategies and some work that we have done in the GS, generalized synchronizations, and we will see that there will be quite a bit of inspiration that comes from Taken's theorem. So here I give just the one reference where generalized synchronizations were introduced, this Kosrev's paper of '95, and you will see that it will be very instrumental for what I will be showing you. So, well, these classical embedding results give us this idea or motivation that, well, if we are able to show that there exists some submanifolds of the state space which are preserved by the reservoir dynamics, driven by the observations of the dynamical system, then probably we have a way or hope to learn also this submanifold. This invariant submanifold may happen to be much lower dimensional than the state space dimension of our system. I already mentioned that it can be a couple of thousands. And then what we will get is two things at the same time. We will get some kind of implicit dimension reduction. And then on top of that, we have a hope that initializing our reservoir system with just initial condition of our dynamical system or just a short history of observations, we will be able to path continue or to forecast. And there will be a difference between what we mean by path continuation and forecasting for dynamical systems. I will spell that out a little bit later. So let me just put myself in this classical setup. We will be working with discrete time differentiable dynamical system, which also admits whose inverse is also differentiable, and then this dynamical system will be defined on a compact finite dimensional differentiable manifold, and let us assume that the dimension of this manifold will be little q. So this will be useful for what is coming. And then for any initial condition, any point on my manifold, the system generates trajectories. So I have also an observation map which renders for me the d-dimensional observations of this dynamical system, and I also need one more object which is phi omega delay map, which basically is a map from the manifold to the infinite sequences of my observations of my dynamical system. And then one more object is something that we already came across in the previous slides. I will be working with reservoir map, which will be a C1 map of a type that I showed you in the very first slide. And then we will be talking about the drive response system, which is associated to observations of a dynamical system. So what I will be doing here, I will be computing or listening the states just using this reservoir map of this type, and well, feeding or driving the system with the observations of a dynamical system. And again, I emphasize that these observations may be lower dimensional. So in particular, this D that I have in my hands, in my data, could be much lower dimensional than the dimension of the original manifold, Q dimensional, on which the dynamical system is defined. And then I'm in the right place to define for you what the generalized synchronization is. So we say that GS occurs whenever there exists such map F from my manifold to basically state space and dimensional Euclidean space in this case, such that well, this relation holds, which ultimately means that evolution of my dynamical system basically in its phase space this is what is driving this drive response system. So in simple words said, I'm establishing some kind of a master-slave relation between the two, and I'm supposed to figure out what would be the constraints or what would be the requirements that I need to impose on this little f, such that my basically slave-master connection between the proxy and my dynamical system is such that it will allow me to forecast to path continue, observing only observations of a dynamical system. So there are some conditions for that, and let me just say that we are meaning by good reservoirs. So we're saying that this f will be good, so meaning that it will correspond to a good reservoir if I will be requiring from this GS something extra. And that's not a little thing. We will require that it should induce a generalized synchronization, which happens to be an embedding, right? So it should be an injective immersion. So we ask the following questions. That's very nice that I'm able to construct this reservoir system, but do these GS in general exist always? Or in particular, can I say that for a given dynamical system, I will be able to find a good reservoir, meaning that I will be able to find such F, which induces GS, which happens to be an embedding. And there are already quite a few complications here. If I'm looking already at this definition, I see that what we require, before I reach the point where I'm asking whether this GS will always exist, or if I'm having a chance to find good reservoir, I'm already, should worry about existence and uniqueness here, because what I mean by that is for any point on my manifold, the orbits of my trajectory should satisfy this kind of equation, and I should have also some kind of uniqueness, right? So that I can put this system to work as a proxy of my dynamical system. So this is what Juan Pablo talked a little bit about yesterday, which is reframed under this equostate property, which is, intrinsic to phi and omega, so for particular dynamical system and observation map. And this is, if you want, existence and uniqueness of states which are associated to observations of a particular dynamical system. So I told you that what we require is the reservoirs need to be good. So I require that this GS exists. There are some results where, for example, in this paper where this notion was first introduced, ultimately the sufficient conditions for existence of GS is just asymptotic stability of your dynamical system. But then there were following works where, it was shown that even though this sufficient condition is something that leads to existence of GS, they may have very bad regularity properties, and we require that it's an embedding, right? So we want very nice regular behavior. So we worried about that a little bit in this paper with Alan and Juan Pablo, where we talked about differentiability of GS, so where we spelled out the sufficient condition for differentiability of generalized synchronization, which basically is something that relates the differential of the state map together with the norm of the tangent map of phi. That's not very useful for this talk, but it's just so that you can go to that paper and check it out if you're interested. However, there is the still embedding that is missing. So how can we inquire, or how we can construct GS such that we know that they happen to be embedding? So there are two ideas. One goes around Taken's theorem. Probably in view of this short time, I will not stop by on that, but it's just a cute result that tells you that if I'm going to be working in this finite dimensional compact manifold, Q-dimensional, it's enough for me to take this truncated, if you want, history or truncated trajectory. Remember, this is the map that I was introducing as basically a delay map for my dynamical system, which just collects the 2Q plus 1 observations of my dynamical system. This map happens to be a continuously differentiable embedding, and what is also nice that it's also a differentiable generalized synchronization, which corresponds to a particular state equation. And this state equation is very cute because you have it linear, and then you have A and C. A happens to be just zero matrix with a basically subdiagonal full of ones, and then the C is just zeros, and the first leading element is 1. And what we did in this paper with Juan Pablo and Alan, which was a subsequent one, is something extra. What we did, we showed that actually, this ESP-F, you can get the same type of Taken's embedding properties if you randomly generate this A and C. So they do not need to have a specific structure anymore. You can just sample them from regular distribution, and you get the same properties. So this is what is done on the linear case. Unfortunately, for nonlinear, as Juan Pablo mentioned in his talk, is still open work, and we actually don't know how to show that these GS or derived conditions under which this GS happens to be an embedding when it's associated to some, a reservoir map which happens to be nonlinear. However, what I will do in this last minutes of the talk, I will tell you that this whole thing, or this preparation that we did in these previous papers, happens to be also useful in applications. And in what sense? Well, if I'm working with good reservoirs, this is what I assume, and I told you for nonlinear case it's not easy to establish, but let's assume that we are happening to work with a good reservoir such that it induces, so the map F induces a generalized synchronization, which happens to be an embedding. Then I know that, well, this set that I defined over here will be an embedded submanifold under F of my reservoir state Rn. And I already told you in the beginning of the talk that we're hoping that this S will be something much smaller dimensional than the original state space dimension. So what I have a hope for is that I do not need to wait until I reach the stationary regime of my state space system if it happens to live in the 1000, 2000 or whatever large dimensional state space, but I have a hope somehow to learn, or if you want to know, to have an idea how to learn this submanifold so that I can use that information and immediately to initialize my state space system using that kind of knowledge. Okay, so we will be placing ourselves in two cases. We're distinguishing between two settings. One is called path continuation and another one forecasting. We're discriminating between the two because one has to do with path continuing the observations of dynamical systems. So let's assume that I'm working with a, I don't know, Lorentz system and I observe only one coordinate out of the three. What I'm interested here is to path continue, for example, only one coordinate for h steps into the future. And another problem will be forecasting of the whole dynamical system out of observations. So I'm interested to know about the evolution of my whole dynamical system. For Lorentz, that would be, I would need to know the evolution of all the three coordinates in time, h steps into the future. The second one is, of course, presumably much harder than the first one because you can have only partial information available. You need to reconstruct the whole dynamical system out of it. Okay, so what we will be doing? The solution will be written down if you want. This is an ugly, long expression, but it does nothing but using the definition of generalized synchronization that I was basically spelling out in the beginning, and just what we mean by the state map. And this will be the solution of the forecasting problem, where I want to pass, or if you want, I want to evolve the whole dynamical system phi, whatever h steps into the future from 0 to h minus 1, and this will be the solution of path continuation problem. So let me start from the more easy one. So if I have this kind of system of equations, which is just a state space representation, if you want, that I was showing you earlier, which I'm feeding with observations, and I'm reading out basically with the help of the so-called predicting readout. So my readout is trained always to provide the one step ahead observation of a dynamical system, which is a problem that you can easily solve. Think of a linear readout map and you are solving the least squares problem where your target variable is one step ahead shifted version of the time series that you used in the input. And then what I notice over here is that I don't know how to initialize, so we will be initializing it with a so-called, what we call a starting map, or this will be called a cold starting map. This is the map that I'm supposed to learn, and which is not available to me, and this is the map that eats 2q plus 1 observations beforehand, before t minus 1, and it spits for me the initialization of my states, which I later on can just rotate and recurse. And then in this problem, we can see that there are more bits missing. For example, I need to know also the inverse of my generalized synchronization itself, and this starting map. And all these ingredients can be learned from data. And let me conclude with some examples on how we can do that. So our problem comes down, again, let me just emphasize, to just learning this kind of a starting map if I'm interested in only path continuation, if I want to path continue only observations of my dynamical system, potentially lower dimensional, or I need to learn a few objects from my data. So my starting map, which allows me to initialize this recursion, and also the inverse of my generalized synchronization and generalized synchronization itself, if I want to solve the whole forecasting problem, if I want to evolve the whole dynamical system into the future, taking the knowledge of only partial information of observations. So this kind of a map that I will be showing you how we are learning. So you are just looking at the observations 2q plus 1 in the past, and you're trying to learn this kind of a submanifold, right, which is embedded by F. So we are doing that with using two techniques. One is inherited from this paper by Yanis, where they are doing the initialization of long short-term memory networks. And they did it successfully for LSTMs. And this is done by the help of the so-called diffusion maps. We show in the paper that it's actually doesn't depend on the method with which you are learning this starting map that you are using to initialize your recursion. You can also use neural networks for that. Now let me show just a couple of examples. We have Prusilator. We probably went through quite a catalog of different dynamical systems. Here we're observing only one coordinate for the two-dimensional system. And then what I will be showing you is that how you can path continue. So here you can see that you are path continuing the system. Let me just show you this, probably the comparison. This what happens. So you have a true trajectory, which is put in blue. You have the gray one, which is initialized with this learned starting map. So basically what you are doing, you are using only 10 observations instead of a couple of, let's say, hundreds that are customary for reservoir systems. If you are working with a couple of thousands of dimensions in the state space, and we're doing that with only like 10 steps, and it already produces very nice forecast based on the path continuation, based on a very short history of observations. And here you can see that if you make it slightly longer, you are, well, getting very, very nice performance. And this what happens if you're doing this standard way of doing it in reservoir computing, where you are not learning the starting map and you are just initializing with zeros, for example. This is the green line. This is what you are getting really far from the true trajectory. And the same thing happens for Lorentz. We're also observing that for other dynamical systems. For Lorentz, it's enough to take only 5 observations, right? And well, no, 7, because we have a Q which is equal to 3. So you need 7 observations in the past in order to perfectly start your state space system. And I thank you for your attention, and thanks a lot. So, questions? Yeah.
So, I just want to check if I'm understanding. So this starting map, that's learning the initial condition to apply, is it?
It is learning, so if I'm going here, so what it does, it just learns a map that brings you from this 2Q plus 1 observations of a dynamical system to this submanifold, which is embedded by the generalized synchronization.
But then, in terms of using this in the reservoir,
yeah. Yes, what you get, exactly, you are getting just your basically initialization for your x0 ultimately, right? So you're not using your initial state as zeros, but you will be using the starting map to construct it. And with little of training preliminary, right, you can get a very nice result on how to obtain this initial starting point without waiting forever until your system warms up or washes out, as they call it in the literature.
Okay, that makes sense. Thank you.
Other questions? Okay, so I take the chance to thank everyone who stayed until the end. And it's very nice to be concluding this great conference, and I'm really thankful to all the organizers for putting it together. It was massive work. I was really impressed. So Frederic is here. I was impressed by how actually, everything worked out smoothly with this number of submissions. It's probably the first time in my life that I could see such a smooth organization process. And I'm really thankful for giving me the opportunity to organize this session. I'm really delighted to be here, and thanks very much. And I'm really happy that these 3 days were just wonderful. Thanks a lot.